Okay, so welcome everyone. So today I have the pleasure to welcome our guest, Marco Canini. Marco is an associate professor at computer science at KAUST. He obtained his PhD in computer science and engineering from the University of Genoa in 2009, after spending the last year as visiting student at the University of Cambridge. He was a postdoctoral researcher at EPFL and a senior research scientist at Deutsche Telekom and TU Berlin. Before joining KAUST, Marco was an assistant professor at UC Louvain, and he also had position at Intel, Microsoft, and Google. So thank you, Marco, for coming. And today will deliver a talk on programmable networks for distributed deep learning, advances and perspectives. Thank you.
Thank you, Sir, for the kind introduction. And I forgot to say, Marco also has a very common name. So it's a great pleasure, and I hope the audience is working.
Nobody's complaining.
Nobody's complaining. All right. So I want to tell you a little bit about the work that we've been doing for the past 6-7 years. So this talk is a bit of a broad talk. I will not go into particular depth into anything, but if you at any point have curiosity, you can just raise a hand, interrupt me, and we can go deeper. And this is work that has done in collaborations with several people at KAUST and collaborators outside. And I would put references about the papers, and everything is linked from my group website. You can also write to me later at any point. So let's get started. So I guess everybody here is familiar with ChatGPT. It came about a couple of years ago, and it is one of the latest breakthroughs. And you probably no week goes by nowadays that there isn't one more breakthrough with machine learning and AI. And this kind of perfect storm arose the past few years because of several key ingredients that enabled this deep learning successes. And so the main observation, if I were to cut to the chase, is that deep learning usually performs better with more data, more parameters, and more compute whenever you're able to increase all these quantities in a lockstep. And this has been empirically observed across many applications, including image processing, machine translation, and last but not least, also with large language models. This is a screen grab from a paper that has introduced this notion of scaling laws for the large language models, where organizations such as Google, Facebook, and so on that have millions of dollars, they can train a lot of models and test what happens if you were able to increase by leaps and bounds the amount of compute, the data, and the parameters for the model. And you can see that the test loss just keeps on decreasing. So what this implies, though, is that at scale, deep learning has to be distributed. And so when we talk about distributed deep learning, what I mean is that our workload, which is a training workload of a particular DNN structure, DNN model, has to be parallelized across many different devices. Typically, this would be GPUs, TPUs, various AI chips, and scaled out to a cluster, so working on many devices across network nodes. Now, if you're lucky, the model size itself, and this has been typically with the scale of image classification models, the size of the model is such that it can fit one single accelerator. Say, nowadays, it's 80 gigabytes. Before it used to be 40, 32 gigabytes. So you can replicate the model into one single GPU, and you can just parallelize in what is known as data parallelism, partition the input data, but you keep the model replicated across all devices. If that is not the case, then we enter model parallelism. There are many different flavors, but the key idea of model parallelism is that you are chopping up somehow this structure, this computational structure, which is the underlying computational data flow of the DNN model, and then you're applying various inter-operator parallelism. And the main key observation is that at scale, typically people would apply different form of parallelization to the workload and just try to get the best performance possible. And this is probably not surprising. Now, if we take a step back, right, it's not just about what happens in the training cluster, how we're parallelizing, but from the point of view of organizations that are training DL workloads, and they want to get the maximum performance from their infrastructure, we also need to be worried about how we map it from the raw data from storage all the way into that training cluster. And usually there is a bit of an impedance mismatch because the data that we are storing is not necessarily the one that we're using for training. So there is some form of load transform that gets applied. This could be data augmentations, normalization steps, meaning other kind of simple transformations that produce the samples so that the samples now are ready to be loaded into the GPUs or whatnot. Now, even though all of those workloads is primarily compute intensive, and there is no denying that, once you take this perspective, you can see that immediately there is a lot of data transfer that kicks in at scale. And so if you're not careful, communication could become a critical bottleneck to getting the best performance from your training clusters. And so then I would like to dive deep into one of the recent trends that we are seeing, which is the trends of GPUs, how NVIDIA over the past 6 years spent 4 generations of their GPUs, they were able to get not only the speed up thanks to Moore's law, but through cross layers optimization, they claim a 26x performance if you compare the H100 to the P100 for some of the workloads. Meanwhile, this is from a report from the Loro DC Ethernet, so something that studies the Ethernet deployment inside the data center. Even though Ethernet, which is nowadays becoming more and more deployed and commoditized fabric for the data centers, overtaking the field deployment, it doesn't have that rate of deployment. It doesn't have that rate of being utilized. And so you can see that there is a mismatch in the practical rate at which we're able to position more and more communication bandwidth in the data centers. So why is that important? So let me take again the case of data parallel. This is the easiest case for parallelization, and it's also the one that affords me to give a very clear intuition about what happens. In this simple cluster with 4 different workers, we can partition the data samples across the different workers, and then, as we said, every worker in its own GPU has a copy of the model. Now, to train the model, we are running an optimizer, stochastic gradient descent, or a variation thereof, like Adam and so on. And at every step of that optimizer, we have computed gradients that have been computed on the data sample, on the mini batch for every worker. And we need to synchronize this partial gradient to calculate the actual gradients that we want to use to update the model. What that implies is that at the end of every iteration of the optimizer, we have an all-to-all intensive communication that could take hundreds of megabytes, even to gigabytes for the models. And we need to do this all-to-all intense communication at every single iteration. So this is a lot of network traffic, quite clearly. Machine learning community proposed to solve this problem with something known as a parameter server. So in their architecture, they would have logically centralized parameter server. This could be one server or multiple ones, but conceptually consider this one box. And at every iteration of the optimizer, the workers will put the gradients, get them aggregated, and then with this new version of the model, the workers could pull the new parameters and then repeat for the next iteration. And some people observed, well, it turns out that this all-to-all intensive communication pattern is something that the HPC community, scientific community, had developed good solutions all along, specifically in what is known as the overuse collective communication. And the idea for collective communication is that you form a logical topology, in this case, I'm representing the rein, and then you run peer-to-peer communication between the workers. Okay, so this is the simplest collective operator, which is more reduced. It has become de facto the standard for a lot of the distributed deep learning workloads. And the reason being, in this case, your deployment actually requires additional servers, additional hardware. Whereas if you are running peer-to-peer communication, you're doing it directly between the machines. NVIDIA adopted the solution and they created something called the NVIDIA NICO library, the NVIDIA Collective Communication Library, where they implemented a range of collective communication operators and all the specific operations runs directly in the GPU. Now, if we dive deeper though, and if we account for the structure of a neural network, which is many layers, right, we can start to see that people were immediately aware of the potential for communication to become a bottleneck, and the way that they, excuse me, the way they started addressing this problem was to the extent possible, maximize the amount of communication and compute overlap, which is one of the holy grail for our programming. If we zoom in into one node, let me illustrate this with a slide. To train a neural network, we do a forward pass. So we compute the activations, we go through a loss function, and then as we start to do the back propagation, we compute gradients. And now you would notice that as soon as these gradients for layer 3 are ready, you can start communicating. So the network can become busy at that point in time. And meanwhile, the GPU can be used for computing the gradients of the preceding layer. And we can keep on doing this. And then we realize that essentially the most critical part of our communication is the one that is exposed relative to the compute, because that particular part of the communication happens to be a barrier before which the next iteration cannot start. So we want to essentially then focus on this part of the communication, and then we can ask, how crucial is that? So because of these technological trends that I was relating to before, compute accelerator performance improvements have so far outpaced the network bandwidth increases. Turns out that for a lot of the DNN models, especially the larger and more recent ones, there is a very significant percentage of time that is just spent on doing communication in distributed deep learning settings. These two profiles show what happens if we go from 10 gigabit to 100 gigabit Ethernet bandwidth between 8 different workers. And this is showing the percentage of time during one iteration that the workload is just doing communication. Exposed communication is demarked with essentially the difference. So this is the dashed part is the overlapping communication. And so this solid remains is actually the exposed communication. And you can see that if you go from 10 to 100 gigabit, a 10-fold increase in bandwidth, of course, the situation gets better for a lot of the models, but especially with the recent ones, like the transformers, the BERT, the actual neural collaborative filtering, LSTM, and deep light, there remains a very large percentage of time that you're just waiting on communication patterns. So this has been essentially our research agenda during the past few years, and we wanted to tackle this communication bottleneck. We proposed several different ways of doing this. The first is something we call in-network aggregation. The second is gradient compression. And then we also looked at the issue of getting data into the GPUs, so data preprocessing. And the common theme underlying these innovations has been the usage of programmable networks. So we have specifically worked at the intersection of synergizing changes and innovations at the network infrastructure layer inside the backbone for doing distributed machine learning. So let me give you an overview about in-network aggregation first. So the trend that we leverage is the fact that networks are getting more and more deeply programmable. Some of you are very familiar. I don't know if this is a common thing across the board here, but both at the level of switch chips as well as the level of programmable NICs. So this is on the NOS side, also referred to as DPUs by NVIDIA and the likes. we are afforded to have some amount of computation that can be carried out for every single packet that traverses either the switches or the NICs. And the idea for in-network aggregation in itself is fairly straightforward. We seek to perform the aggregation of the gradients along the network paths, so that the data that sits in any way needs to be transmitted, you might as well get aggregated inside the switch instead of having to be sent in a peer-to-peer fashion across the network. And the benefits are threefold. Most importantly, one that we seek to obtain is an improvement to the end-to-end throughput, that is how many samples per second we can train the model at. Moreover, we can perform aggregation at what we call sub-RTT latency, and in a way that is independent of the number of workers, which is important because this does not happen if you increase the size of your ring or reduce. And finally, we can also reduce the traffic on the network fabric itself, leaving leaving bandwidth for other workloads to compete with that traffic. So our main design is something that we call the switch ML. It's a co-design of distributed machine learning together with the network it supports that it needs. And we base this off the Barefoot Tofino chip. So this is work that started really in 2016 as we acquired one of the first chips that came to market. This was before Intel acquired and then more recently killed this platform, unfortunately. At that time, the first generation of the Tofino was capable of 6.5 terabits per second of programmability. But of course, you could only do very limited amount of computation, and you would have only very limited amount of storage. So you cannot really think about creating a parameter server appliance with this type of chip. Moreover, there is no floating points, which is the backbone for training a neural network. And because this is a network, ultimately you have to deal with the possibility of packet losses either induced by congestion or by corruption. So in our design, we tackle these challenges and we create something we call the streaming aggregation protocol. I'll spend a little bit more time on that in a moment. And then we make the best use of the combined switch host architecture, delegating essentially to the switch only the simple things that it can do well, namely integer operations, requiring some level of quantization, and then relegating to the host the quantization itself and figure recovery protocols that are custom made for this co-design. Last but not least, because we want everything to work super fast, we have to rely on RDMA to get the data outside of the GPUs and into the network, but that meant also implementing RDMA inside the switch in order to enable that type of communication. So let me now overview the key technical innovation that we propose with SwitchML, which is the streaming aggregation protocol. So I'll just illustrate this with the simple case of two workers for presentation's sake, but you can generalize it easily. So assume that these shaded areas represent our gradients that have been partially computed of mini batches, and then we split them into various blocks. And we can view the switch as a pool of aggregation slots, where every slot in the switch represents an aggregator of one block of gradient values. Let's say this could be 1024 gradient values. Then we can essentially, in a deterministic fashion, map those blocks of gradients into slots on the switch and start streaming the data to the switch. And the switch, as it receives the contribution from multiple workers, knows how many it should wait for. And once it has aggregated fully the contribution from the different workers, it can broadcast back the aggregated packet. At that point, receiving one of these aggregated packets serves implicitly as a flow control signal that says, okay, one slot is now available at the switch, so you can send the next corresponding block for deposition or for that slot on the switch. And so this is a streaming operation in the sense that we are coupling together the workings of the workers that are streaming the data in the switch, and we can leverage a full line rate, the communication between workers and switch, which in this illustration, for instance, assuming that this was a 100 gigabit link, you would have every worker sending bidirectional 100, sending and receiving 100 gigabit throughput. Okay, so this is our key innovation. To make it all work, as I said, we had to combine the capabilities of the host and the switch. And so relegating to the switch fixed point integer aggregation, which meant devising some form of quantization to convert floating point numbers into integers and dealing with failure recovery. Now, this may get, however, some eyebrows raised because, as you know, if you work with integer quantization from floating points, you might have a lot of numerical error. So we wanted to minimize this type of quantization error. We take advantage of the fact that the gradients are already grouped into blocks, let's say 1024 values. So we can compute a scaling factor in advance in a look-ahead fashion for every single block so that we minimize the representation error of making the conversion. And then it's just a matter of scaling into integer and then back into floating points. And we collected a lot of empirical evidence that this form of quantization is actually effective and affords us to train a neural network with similar accuracy in a similar number of iterations as in an unquantized level. This is one example in which you can see that these lines between the switch ML and the baseline, which draws unquantized training, are literally the same, and we have many more evidences.
So it's like one scaling factor per block of whatever before evidence.
So the thing is tunable.
Okay.
Yes.
I was asking, did you try different block sizes?
We also did. Yes, we also did. We also did this. Yes. So what it turns out is that gradient values tend to be fairly small in terms of the distribution, and if you typically if you have a small enough block size, the representation error between the conversion from the floating points and integer tends to be very small. Yeah. So then the next thing, obviously for evaluation becomes, is this effective and does it produce benefits? So we evaluated SwitchML in comparison to the NVIDIA Lincoln library, the de facto standard industry library for doing distributed deep learning. And we evaluated it into two settings at 100 gigabit with P100 GPUs, where if you consider nickel being the baseline here, so the 1.0, we noticed that we could get an advantage, a training interval advantage of up to 2.7 times for deep light, which is also the larger model that we had. And then this kind of speed up benefits could get as little as just a mere 13% for NCF. The reason, though, in this particular setting is that we were using a very, now I would say, old P100 GPUs in a very fast network. It was not very representative of the newer type of clusters that we see. So we scaled the GPU synthetically to perform essentially 10 times faster. We repeated the experiment. And at that point, we found that for the majority of the workloads, we could get a speed up that is close to a 2.x. And 2.x here is also not by coincidence, because 2.x is by design the speed up, the theoretical speed up factor of SwitchML as compared to an optimal implementation of ring or reduce, because ring or reduce has to send twice the volume of data for doing a full execution of its algorithm. The second main advantage, though, of SwitchML is that also its performance does not depend on the number of workers. That is, the caveat is, if you can connect the workers to the switch, that is, if you have the bandwidth, then every worker has dedicated line rate transmission. And this is analyzed with this result in which we have throughputs higher is better. This dashed line here represents the max RDMA goodboot that we can get. And you can see the SwitchML, the blue bar, stays very close to the max RDMA goodboot as we scale from 4 to 8 to 16 workers. The implementation of nickel instead would not only trail well behind that maximum throughput, but also, as you can see, that as you increase the number of workers, its performance also decreases. So we were, technically, we were still bothered by the lack of floating point operations on these programmable switches. So I don't know what happened. Oh,
Test the screen.
that is not me. Okay. So a year later, we also proposed in an NSDI paper a way to implement native floating point, or approximate, I should say, floating point support in commodity business switches like the Tofino architecture. We were pushing actually for Intel to adopt this type of low-level modification to their architecture. They probably would have made it in the next generation of the Tofino chip, except it was killed, so never visible. But in the evaluation that we did, had it been possible to build that chip and so on, then there would have been benefits for our design, specifically for switch amount. Then you would get rid entirely of the quantization. In our implementation, the quantization was happening inside the CPUs, so we would free up our CPU cores. Okay, now with switch amount, we had a very solid story about what to do with all this gradient data, particularly without even looking at what the data contains. But then we investigated, okay, what is actually the gradients and what is inside the gradients? And we noticed that for a lot of models, particularly the one that have very large embedded layers, the gradients values can be actually very sparse. That is, you have a lot of zero or close to zero coordinates, and it makes no sense to send them over the network to have them aggregated. So then the question became, how can we efficiently aggregate sparse gradients? So building upon our expertise with switching, we extended the design and we created a sparse streaming aggregation protocol that we call omni-reduce. We kept the core idea, which was to split the gradient data into blocks, but in switching we had to do it to map into the slots inside the switch. So the switch was given that constraint. In this case, the idea of splitting the gradient data into blocks was about having an efficient way of skipping over blocks that contains sparse data. And so now you had also a little bit of a variable to decide how large the block should be, right? In the limit, you would have a block of size 1, but in that case, you also have to send a lot of metadata, or you could try to make the block size as large as possible. And the issue with that is that as soon as there is one coordinate that is non-zero, the block cannot be considered a zero block. Now, in this illustration, just for the sake of representation again, there are two workers, and we replace the switch with something we call the aggregator. In this particular work, we did not implement it with the switch because we were not sure that the complexity of the algorithm would afford us to implement it in the switch. Later on, we found out that there was a variation that we could do and map it into the switch. But for now, for the sake of argument, I think of this as a server, and later I will tell you that this could actually be a smart link. So what we do is that we stick a bit of metadata in each block that says, relative to that worker, where is the index of the next non-zero block? And that this is going to be one thread of computation. So the aggregator also has some metadata to consider the per worker next non-zero block and the global next non-zero block. And with that information, it affords every worker to know at what point in time it has to send its next non-zero block. And then this being one thread of computation, we're just essentially running these as per many aggregation slots that we could have in order to saturate all of the bandwidth in the network. And so if we do this, our main advantage comes from sparsity, which then meant we made a comparison against switch ML, considering models where a certain fraction of sparsity does occur. Deployed, if you remember, was 99% sparsity. So for deployed compared to switch ML, we could see 2.23x. And this comparison was made by re-implementing switch ML in software to make sure that we had a fair way of comparing between omni-reduce and switch ML. For other models, the the advantage was lower, and obviously it depends on the proportion of these zero blocks that exist. And this was also an interesting side of our story, because in the process of creating on reduce, there was a company called Meituan in China that contacted us based on the switch now paper, and were very interested in using that. But then we told them about how it was implemented, and found that they would need programmable switches. They said, no, we already bought the switches, we don't want this. And then we told them, okay, have this, and this is in software. So then we're happy, and they ended up adopting it for some of their recommendation models, where they noticed that they had a lot of sparsity.
Like they need to have a huge overhead or a simple overhead in maintaining the metadata for grading, so to identify which blocks are sparse, and which blocks are not, like you do training. Is that a significant portion of?
So there is some amount of overhead. You're right. So the story here is in the OmniReduce paper, we will do the following: we'll let every worker compute the gradients. Then within the GPU, we will run a kernel that scans through the data of the gradients, which typically is about we react at the level of the thing that PyTorch calls the buckets. So it's about 30 megabytes worth of data. We will run a kernel, check which block, depending on the block size, which blocks are considered zero blocks and which are not. And we would construct that one as a bitmap. Then we will lift the bitmap into the CPU memory, and then the communication will start. So at that point, you have no further overheads because of that. Yep. Okay, so for the sake of time, let me also not bash too much about cages first, and just skip that, but that is just not competitive. So one issue that we had that we were not too completely happy though with OmniReduce was the fact that now we couldn't do it with a switch, and we need to have servers to run these aggregators. And we noticed that there were indeed some overheads, some CPU utilization overheads in all the I/O. Particularly if you wanted to do the bitmap in the CPU calculation instead. So the question we asked is, could we instead leverage smart NICs, which are becoming more and more ubiquitous, and nowadays also a lot of the worker machine with many GPUs, if you buy them, they have not only multiple NICs, but they have also these programmable NICs, NVIDIA case being the BlueField. And so the benefits that we could count on would be to save CPU cores, improve scalability, and get away without extra servers. So for lack of a better name, we're going to call this project OmNIC instead of OmniReduce. And we are really trying to rethink our system and going from this diagram here to that diagram where one of the NICs on board is a smart NIC, and we're going to delegate the aggregation logic that inside the smart NIC. And we tried to do this with, we have a upcoming SICOM workshop called, I don't remember, it's Networking AI, something, anyway, Lake workshop for SICOM. So there's a short paper that you'll be able to read online. So in this project, we are working with the NVIDIA BlueField, which if you're familiar with it, you know that it's one of this newest generation of smart NIC. It's not the latest, but it's sufficiently new. It follows the trend of having a fast set of NIC cores, and then a system on chip with ARM cores that are not necessarily the strongest cores, but they're kind of like good enough. And there's 8 ARM cores. But the issue that it has is that just the memory bandwidth is just very, very limited. And so if we were to process a stream of data at 100 gigabit per second doing just this aggregation, we benchmarked this, and we found that we would need 43 gigabytes per second of memory bandwidth between those ARM cores and the memory on board, whereas this particular board only has 10 to 6 gigabytes available. gigabytes per second. So in this project, I have a very clever student, Tonju, who figured out two things. One is this board has an undocumented feature, which is the direct cache access feature that allows you to work on the last level cache through RDMA. You can populate things in the last level cache and avoid certain memory operations, certain writes and reads, if the working set stays inside the cache. And so we optimize the design of omni reduce for that feature. And in addition, we embraced wholeheartedly RDMA, including features like the scatter gather and shared RDMA queues to gain them, to squeeze essentially the last ounces of performance out of the board. And we've been successful so far. So this is a key result that compares having a direct cache access optimized version of OmniReduce and then running it either on the Bluefield tool or in a CPU server with different block sizes. And what you can pay attention is the Omni, which is either the green or the blue lines, are always below the CPU server. And moreover, the performance of running on the Bluefield, which is the dashed line, matches the one that runs on the solid line, which is the CPU server. And this is a latency block as we increase the data sparsity, so lower the better. And so you can see that this board in and by itself will be capable of actually aggregating the data. We don't have end-to-end results for this, primarily because our dear friends at NVIDIA wouldn't really sell us nor donate to us enough Bluefield. So we're doing the project with just a couple of adapters, and it turns out it's very difficult to get end-to-end results in that way. But these results are certainly very promising.
Marco,
Yes.
so when you say with the direct cache access, is you access the last level cache of the host directly from the Bluefield tool, or
No, I mean the last level cache of the ARM in the SoC.
I know that in the Bluefield 3, they have this EPA architecture with a set of RISC-V that they,
Yes.
you can potentially,
which do not have floating points. So we could tap into those, but then we forecast that there's only an issue, which is we will lack floating point, which is a different set of issue. But we might have also some solutions. The issue with the Bluefield trade is that I've been trying to get my hands on one of those since January last year, so 2023, and now we're June 2024. So.
But I also heard that the memory some system of the RISC-V is pretty much limited. I mean, it's very limited. So you have layer 1, layer 2, layer 3 cache on the RISC-V, but then the bandwidth that you can get is very low. But I'm not sure. Yeah.
So to the memory bandwidth, we have a new design. I didn't go into the algorithm, but you can read it in the paper. That obviates to the issue. But most of the benefit really comes from having done the redesign of the algorithm so that you keep the working set so small that it fits into the last level cache. Okay, so now I'm going to switch gear and I'm going to talk about a completely different approach, which is gradient compression. So if you cannot do switching out, you cannot increase the bandwidth or leverage the sparsity, what you can do is that you can try to shrink the data volume so that you address the network bottleneck. When we talk about data compression in the context of distributed learning, it's always lossy compression, which introduces a trade-off between the training throughput and the accuracy. And there are many ways of doing compression. You could do quantization, you could do sparsification, where you, for instance, sample top K values by magnitude or lower rank decomposition. So there's a very wide literature here. And there are obviously some implications. On the good side, a lot of people who are much theoretically inclined have studied this and have promoted convergent guarantees where they can recover the same asymptotic rate of SGD. On the system side, though, if people propose very complicated algorithm, it could be that the time it takes you to compress the data is more than the time by which you could have sent all the data. So you're not going to get a real speed up. So I would claim you can get a real speed up if and only if the number of iterations that you need to do and the time per iteration with compression is less than the number of iterations that you had originally and the time to do one iteration without any compression. And in order to demonstrate this point, I'll quote one study that we did in a framework we call GRACE, where we implemented 16 compressors from the literature chosen to represent the broad spectrum of all the approaches. And this is one workload. This is a very busy plot. I don't really expect you to take away every single thing here. But let me just illustrate 2 key points. One is, if we consider throughput, so this is a relative throughput normalized to the case of no compression, and the y-axis is always going to be accuracy. If you are on the left-hand side of that one, it means that your compressor is detrimental and is not giving you any speed up. And you can see that there are many, many points here with different compressors that actually don't provide a speed up. Number 2, unlike what common wisdom would suggest, volume and quality not always correlate. So sometimes compressing more might actually not be the worst idea. This does not hold for all compressors, but actually it does occur. And then last but not least, this is one single workload. In the study, we had many workloads, and we obtained a key result, which is not very surprising. There is no one size fits all. So ultimately, we could take away that people are not nowadays, despite all the papers that have been produced in this area, and not using compression, because it's actually very difficult to employ. And it's also difficult to know where it's going to be beneficial in terms of a practical implementation. So motivated by this, we proposed our own, let's say, works in this space. And here I'm just going to put up a slide with a few pointers. So if you are interested later, we can discuss more, or you're welcome to follow up offline. So natural compression is our quantization scheme in which we were trying to synergize in-network aggregation with compression. We developed a quantization scheme in which every gradient and coordinate would undergo stochastic rounding to the closest power of 2. Why the closest power of 2? Because once you have that in the hierarchical representation, then only the 8-bit of the exponent and the bit of sign are what you want to send, and the mantissa you have a whole bunch of zeros. So then the good thing is that this is actually integer, so we can send it to our switch channel and do integer aggregation and send in 9 bits instead of 32. We also worked on a very fast version of doing compression by sparsification. So if you're using something like K, it involves a kind of sorting, so it can be slow. Rather than doing K, you could do threshold sparsification. If I give you the exact threshold that you need, you would obtain exactly the top K coordinates, but in a much faster way, because you only need to compare the gradient values against the threshold. But the issue is that estimating the right threshold is hard. So our main contribution in this work was to figure out how to do a good job of estimating the threshold. And there is quite some theory involved in that. But then the massive gain that we saw was up to 41 times in a benchmark that says what is the time to the final accuracy that you want. We also consider conditions in which would be typical of cloud settings, where the bandwidth actually changes between the workers, and therefore you don't want to pick a fixed compression ratio. You would rather want to adapt your compression level to the network bandwidth. And most recently, we're pushing for something that we called practical floatless quantization, because we figure out that it is very nice if we can work with a special arithmetic in the compressed version of the gradients. We could adapt that as a modification to nickel or as a modification to switch ML. The issue is that typically when you quantize the gradients, now they exist in the quantized form, in the quantized data representation, you cannot simply aggregate them. That is, you don't have a native operation from the instruction set that you could apply. So the quantization that we propose that we call it floatless is first we identify the global norm across all the workers, and we normalize all the gradients. And at that point, we could do either standard dithering, so linear levels, and we have fixed point arithmetic, which could work, or we could do exponential dithering, like in the natural compression case, based on the powers of 2. And in this case, we'll need a custom reduction operation. And we saw that this is beneficial even in the case of a very fast fabric for intra-host GPU communication, like NVLink, with up to 450 gigabytes per second of directed bandwidth, or obviously more importantly for a bus that is as slow as PCI Express in comparison, or in Google Cloud, which I don't know exactly what they have on the network stack, but that one is an experiment running many nodes in their setup. And for the case of DeepLight, this is a speed up of almost up to 3.5x. So let me recap here. So we have observed this issue of the network bottleneck in training, and I showed you 3 different solutions: network aggregation, sparse collective communication, and trading compression, and for each, what our approaches have been. And importantly, I wanted to stress that only the last approach actually involves a trade-off between the training throughput and the accuracy, whereas for the first 2, that one is not required. This one is a replacement to your collective communication language. So if there is any more questions at this point. Okay, so I'm gonna segue back into this diagram here of the pre-processing that needs to happen. And we took interest in this problem because people from Meta actually documented for the workloads the fact that it is more, there is more power that goes inside pre-processing for at least one of the workloads than there is power that goes into training. So that doesn't seem to scale very well. And they also reported that the growth of the online ingestion bandwidth is exceeding by almost 2-fold the size of their storage data sets. So obviously, if you take the operation of a cloud provider or someone that is in the business of having all these resources for training models, GPUs are the most expensive components in the cluster, and you certainly want to keep them busy. What that means is that whatever pre-processing you're doing on top of the data, it has to finish before the GPU requires the next batch of data. A problem that would otherwise be called a data stall. And the solution to this is to ensure that the pre-processing rate exceeds the ingestion rate of the GPUs. So in order to achieve that, still the same study from people at Meta reported that they would use between 9 to 55 CPUs for every GPU worker, which seems like very expensive and energy efficient. And by the way, the way that they do this, and the way that, the reason for which this is actually a distributed pre-process step that is not occurring within a training cluster is for the generality, because different workloads actually do require different transformations, different operations. So it's very hard for them to dimension the exact number of CPUs to stick into every GPU worker. But taking a look at the transformations and the operations that we're doing, we found like, okay, these are very simple operations, so could we use in-network computing? And because of our expertise working with Tofino 2 in particular came along, we tried to implement a subset, as many as we could, of these transformations inside the Tofino 2 chip and execute them as network function packet by packet. Now, as you can see, we actually only got around to implement the minority, and I think maybe people with FPGA background could tell me maybe you could do it with FPGAs, it would be better, and probably you'll be right. Still, we pursued the idea of deploying this on programmable switches. And this is more or less the most positive result that I could give you as an upper bound. So I want to caveat these results in the sense that this is probably a very optimistic margin for improvement. We actually don't know what that improvement in practice will be, because despite many efforts, we could not get a hold of the real workload. So we had to make many assumptions about what is a workload for transformations, and we just created random transformations affecting some parts of the packets. We just made many assumptions. However, when considering an implementation based on Intel Tofino 2 of those transformations I showed before, and the morally equivalent transformation running on a not so fast CPU server based on a DPDK implementation, there is a 65% margin for improvement in terms of gigabits per second per watt of data preprocessing efficiency. This is the direction that we're still exploring, but I like to always pause at this point and say, does anyone in the room have a real workload that we could have access to, because we have so far failed. Okay, so let me come full circle though, because I started with ChatGPT and LLMs. And if you pay attention, most of what I talked about wasn't really about LLMs, but as we know, everything nowadays is about LLMs, right? Including just in the movie, right? The speed at which machine learning research is happening. I will make an analogy. That's seen. So LLMs definitely require distributed deep learning, and they pushed us beyond data parallelism, right? You cannot fit these models because they're way too big. It is even rumored that GPT-4 will already have reached 1 trillion parameters. And there's no way that you can fit all of these parameters inside one GPU. So then obviously we need to look into model parallelism. And there are actually two proposals for how to do it. One is, sorry, I'm running ahead of myself. Okay, this is just an analysis of how many GPUs you would actually need, like what's the minimum number of devices that will be required. And there are different ways that you could match that. So one is, if you're a good engineer and if you're willing to dedicate all the effort, you can take your model and implement pipeline, tensor, sequence, parallelism, mix and match them, and try to match the particular neural network structure to the best performance possible. And this would require significant engineering. The other perspective that people are using is something that's called fully sharded data parallelism that is emerging as an alternative. And this is promising, and it's becoming popular because I can take the model in an unmodified way and run it on many devices. And the reason is, when you execute the forward or the backward pass of the network, at any one given point in time, you really only need one layer of the network. You need the layer that you're computing over. So what do you do? What do you do for memory management? You're basically like paging, right? You're swapping in and out the state that you don't need. When you don't need certain parameters or activation, you shard them, you put them in one GPU in the system. So collectively, the union of all the GPUs are storing all the parameters and all the model state in terms of activation, optimizer state. And during the computation, every GPU would bring back into its own memory all the parameters and activation and so on that it needs for that particular stage of the model. This is called fully sharded data parallelism. It was maybe a rebranding. Originally, it was introduced by the Deep Speed team at Microsoft. It was called the Zero Optimizer. So, what is the problem of this Zero Optimizer? Is that it actually aggravates communication. Because if you consider that M is the number of your parameters, to do FSTP, you're gonna have to communicate through M, which is a lot. So for different models, say even something like GPT-3 or Megatron, we're talking about at every iteration of FSTP, there is a few terabytes of data that need to be communicated. And doing that at line rate over a 400 gigabit network, right, would also still amount to a few tens of seconds. So then, once again, even in the land of LLMs, performance is actually constrained by communication bandwidth. Specifically, in this realm, inter-node communication bandwidth really becomes a bottleneck. And these kind of frameworks do take advantage of the conditions in which the bandwidth needs to be very well balanced between in the cluster for inter and intra-node communication. Otherwise, as soon as you start to involve things that are not well balanced, your throughput just drops by more than tenfold. And this is something that we saw in papers reported and we confirmed ourselves. Let me, for the sake of time, let's just skip over this. So in this round, there is one more thing which is problematic, which is it's actually very hard to correlate the benefits of increasing bandwidth at some point in the workload to the end-to-end throughput. And I'm going to show you two examples of this. One is a real experiment that we've done with a GPT-2 model over 2 nodes, each of which had 3 P100s, and we're using a second generation NVLink. But no, actually, that was a first generation NVLink and 100 gigabit Ethernet across the nodes. Anyway, the point here would be when we increase the bandwidth between the nodes to between 10 to 100 gigabit Ethernet, the improvement in deflops is a mere 4x, despite a 10x bandwidth improvement. And also, similarly, the iteration time also drops by about 4x. Then we're exploring what happens if we apply compression, given that with this kind of large language model, you can still apply compression both in terms of model state as well as gradients. This is a simulation, so I want to caveat that. But in terms of throughput, this would actually be something that tells us at least what we should expect. We assume no compression over it, so it's in that sense it's a bit of an ideal case. And in this case, we consider very modern settings. So a NVLink bus with 450 gigabytes per second for the intranode bandwidth, and then we vary the internode bandwidth by 100 to 800 gigabit per second. And we focus on the exposed communication only. So we measure that one with a simulator that's called AstroSim. And compression is a static ratio of 25% of the original volume. So once again, the bottom line is that there are gains, but it's very hard to judge the proportionality to network bandwidth. And consider this. So this is the baseline. The y-axis here is the amount of exposed communication time per iteration in millisecond. So lower is better. And you can see as we increase the internode bandwidth, this number gets lower. So it means that the iteration time, the amount of communication in each iteration time gets lower. But at some point, it saturates, right? So you can see if we were to apply compression, internode compression, we would need as little as 100 gigabit, and we would already match the performance of 800 gigabit network. But then something interesting happens, which is in the case of the intranode compression, right? If we apply compression before using NVLink, in this case, and this is the full workload, right? So this is not just compression over an NVLink. We could keep on scaling, and we would get the most benefit at 800 gigabit internode communication. And when we apply compression to both types of communication, then we could lower that again, but then at that point, we will need only 400 gigabit of bandwidth. And so as I said, I want to carry this. This is just a simulation result, so I do not know that it would hold up. But what it reveals is that it's actually very hard to know where you would want to play with the different optimization and different compression in this case for this type of workloads. And this leads me to more or less what is my future work, what we're working on today, which is we've come to this scenario in which the type of research that I showed you before is very hard to do in this new world. I don't have access to thousands of GPUs, and if I did, maybe I would use them for other reasons than this. But nonetheless, scientifically, and both as an intellectual curiosity and as a practical matter of importance, there is this problem, which is we want to conduct a lot of what-if analysis cheaply with high fidelity in order to optimize deep learning workloads at scale, particularly for large language model, but this is very hard to do. We could turn to simulation, okay? But as we know, for simulation, there are several caveats, especially when it comes to fidelity. And simulations is always about capturing enough details of the problem. You never know whether you capture necessarily all of them. So we turn instead to emulation, in which we aim to directly replicate the end-to-end system behavior. And the key benefit of this type of emulation that I'm about to present to you is that we can run the real code, implement direct modifications, and observe the behavior. So in a way, we can also complement the simulators that exist nowadays. And our key insights in the specific area of deep learning, distributed deep learning, and large language model is the following. If you take one of these workloads, given the amount of parallelism that happens, right, there is more or less, I would claim always a slice of the workload that represents one unit of parallelism. And I can focus on running that unit of parallelism in a virtualized world, in an emulated world, in which essentially the real workload operates there and everything around it has been emulated. And we can do this for these type of workloads because the natural boundary here is essentially equal, is connected communication. So we created this approach, we call it Neurona Box. We have a short paper on archive if you're interested. And what we're pursuing is, at this point in time, was just a feasibility. It turns out that hacking into nickel is quite something, but we really wanted to demonstrate that this is doable. And so we have a proof of concept. We were able to run a 2-node setup. In the real node, we run a modified PyTorch, a modified networking library. So it's everything that runs there does not know that it's actually not a real distributed deep learning job. In the Neurona Box node, this is the emulator. We modify nickel, we modify PyTorch, we strip out everything that we don't need, and we were measuring some simple metrics, and we saw that we could replicate the behavior of the full system with less than 1% error margin in this case. So as I said, this is preliminary, but I think that this is a good tool we have both for researchers as well as for industry, partially pave the path for a lot of the new optimizations that are to come in this area, so that we can more or less have an affordable way of actually working out where to focus our efforts and where to put optimizations. So let me conclude here. Sorry for being a little bit over time. So we started this journey. Deep learning we saw requires compute, data avalanche, and the more you can throw it, the better probably it's going to behave. So distributed deep learning becomes a must for large models, and there are many forms of parallelism that occur, which are typically combined data model pipeline patterns. In doing all that, it can be that network communication then becomes the bottleneck, despite the workload being very compute intensive. And I presented to you in network aggregation, faster collective that daily supports sparse data and gradient compression techniques. I also touched on the problem of data ingestion being demanding for bandwidth and how an in-network compute approach could actually be more efficient. And last, I finished with the issue of LLMs and the fully charted data parallelism approach. And nowadays, our follow-up research is this neuronal box. So if there is anyone interested, feel free to get in touch. To acknowledge a long list of collaborators, but I'm not going to read all their names. All these works will not be possible. And with this, thank you, and see if there are any other questions.
All right. Are there any questions here or online
There
questions?
was one in the chat. There's a message from.
Yeah. I think there is a question. Antonio, you can ask the question directly if you want, or
Okay, yeah. Can you hear me, everybody?
yes, we can hear you.
Okay, thank you, Sebastiano. So thank you, Marco, for your presentation. It was very great. I work a bit on federated learning rather than distributed deep learning. And in federated learning, we have this kind of technique to reduce the amount of data that you want to share so that we reduce the transmission overhead, which is doing model pruning. So rather than sharing all the model, because for sure
It's a little bit hard to hear you.
deep learning is a bit different, doing in a different way, but rather than sharing all the model, you just perform some pruning.
Antonio, can you repeat the question from the beginning because we couldn't hear you?
Can you see? Okay, let me see if I can change my audio settings.
No, I think the problem is that
Can you hear me better now?
Let's give it a try.
Yeah.
So I got it. It's model pruning in federated learning.
Yeah. My question is how this cannot be applied in the distributed deep learning, or if this is still a thing in distributed deep learning.
It's a very good question. So as far as I'm aware, some people have in the data center setting, which is essentially what I've talked today about is most relevant. I've seen people working on independent sub-network training, which is a different field than distributed learning, and it's also separate from federated learning. But in the independent sub-network training, the idea is that you decide potentially at the granularity of every iteration, which subset of the network, meaning which subset of the neural network you're going to train for that iteration, and the workers are going to just work on those parts of the models. And it's not exactly model pruning, but my understanding is that in that case, you would only train a sub part of the model, and then it's about how you aggregate those model updates. I've seen that one being proposed for data center settings, but I haven't seen model pruning itself be proposed. However, if I take a step back, I do think that in the not so distant future, there would need to be a bit of a hard look to try to synergize better between the vast amount of federated learning algorithms that have been proposed recently, and also what's going to happen for very large scale models. If not because of anything else, the fact that even when it comes to training a model with a few thousands of GPUs, it could become very difficult for those GPUs to be physically located in the same zone, in the same data center. And at that point, the latency between different GPUs, different machines would be not only heterogeneous, but it would also be long. So if the latency is long, then you're more akin to a form of federated learning algorithm, where you want to do more local work and then aggregate. So I think that there is room to try for some of these ideas in this space, but you need to pick, I think, your the setting to be an appropriate one, right? To be good. And again, will you be able to evaluate this without, getting 1,000 GPUs? So maybe, we should talk more, and you could be one of our first users for Neurona Box.
Antonio?
Yes, I'm sorry, but I don't know why, but for all the presentation, the connection was perfect, and now I only heard the half of what Marco was saying. But I believe that, by the way, thank you for the answer.
It is recorded, so you can look at the recording.
Yes. Yeah, you're right. Thank you, Marco, in any case. I'm sorry for the connection.
No problem.
Thank you.
Okay. Are there any other questions?
I had a question about the last part about so in the full sharding idea, basically you make no assumption on where you put this data here and who would request the data at what order.
So it's called fully sharded data parallelism, because the type of parallelism is essentially the same as data parallelism. So every GPU will go in lockstep, right, at the same place with every other device, forward and backward. Right. Where the data resides, it's fully sharded. So I'm not sure how they identify who holds what, but I think it's a very simple mapping problem. You just partition the model and you decide this chunk of the model resides on this GPU, this chunk resides on that GPU. And then whenever you need it, and you need to fetch it back.
Because in my mind, a lot of the optimization on bandwidth could be like placement.
Yes, so there are potential for optimization there. So Microsoft has a new paper that was published in I think ICLR this year called 0++, in which they were trying to make 3 types of optimizations to this to how to move the data. And then I've seen some other work, I don't remember now, in which they were also saying, I don't necessarily need to only shard the model state in a fixed way. I could replicate the model state so I can make more copies, so that then I can bring it in faster, and not every part of the state basically is created equal. So there could be pieces of state that are more important, so I replicate more, other parts instead less. But yeah, you're right, there is potential for other types of optimizations in there.
All right. So I think we can again thanks Marco for this interesting talk, and also thank you, Marco, for hosting it. So thanks to all Marco in the room. Okay, thanks again.
Thank you.